Welcome to Brain Vision.
Okay, so in this problem, we have two boxes that are connected by a string, and then also a net force being applied on the box that is on the right. And that force is being directed to the right. So we have M1 over here, and then M2 over here. And then again, they're connected by a string that is taut, has a tension T. And then we are applying, oops, applying a force to the right, and we're calling that F. Okay, so part A is asking what the net acceleration on the 4 kilogram crate, so that is the first one, um, given the fact that the acceleration on the second crate is 2.50 meters per second squared. And just so that my labels match the ones given in the book, M1 is 4 kilograms and M2 is 6 kilograms. So they're connected by a taut string, so this part is pretty easy. And therefore, the acceleration of the second crate will be the same as the first one because they're moving together. And that is given by 2.50 meters per square second. So that is part A. Okay, part B is a little bit more involved. It is asking us to draw a free body diagram for the crate on the left. Let's go ahead and switch colors now. And there will be several forces acting on M1. Not all of them are important. But starting off with the most obvious one that's always present, and that is the force of gravity. It's going to be balanced by, sorry, this is supposed to be in the opposite direction, balanced by the normal force acting on crate 1. We'll call that N1. And then M1 is also feeling a tension force to the right that's coming from the string. Okay, so we have all our forces. Now we want to know what the force of tension is in part B. And that is going to be equal to applying Newton's second law in the horizontal or x direction. It's going to be equal to its mass multiplied by its acceleration. So we know both of those values now, so we can plug them in. 4 kilograms and 2.50 meters per square second to get, at the end of the day, a total of 10 newtons. Right, and then we don't even care what the normal force or the weight is. All right, so let's do part C over here. Part C is similar. We're going to draw a free body diagram for mass 2, and then we're going to say what the direction of the net force is, and whether the tension or the applied force is greater. All right, so let's just get started with that free body diagram then. It's going to look very, very similar to the previous one. Sorry, this was M1G earlier, because over here it's M2G. That's the weight. There's no vertical motion, so the vertical forces are going to balance each other out, and that is N2 with mg. There's, of course, the applied force, which I'm going to draw a little bit longer, so that's F, and then this tension force, which we don't need to put a subscript on because it's the same tension force as before. I'm just exaggerating how short it is because our system is moving to the right, so we do need the F vector to be longer than the T vector. And those are the four forces acting on mass 2. So if we were to tally up all these forces, we would see that F2 points to the right. They wanted to explicitly know the direction. Go ahead and write that out in words. And then they want to know the magnitude of F compared to T. Oh, sorry. And then this is not F2, but F net, the net force on F2. Sorry, that says net. F net points to the right. And then the other thing they wanted to know was, the relative magnitude. Of course, the applied force has to be greater than the tension force, or else the system would not move to the right. So we know that. And then lastly, in part D, we want to know what the magnitude of that applied force is. So we can do a similar procedure to in part B, and then tally up Newton's second law for mass 2 in the horizontal direction. So those forces are F minus T is equal to m2 times acceleration 2. So before we plug numbers in, let's go ahead and add t to both sides. Rearrange a little bit so that we can isolate and solve for f. So for t, we solved for earlier, and that is 10. Add that to the mass of m2, which is 6.00. Same acceleration, 2.50. That's going to end up being 10 plus 15, so that gives us 25.0 newtons. All right, and then we are all done.